Hello. Let me introduce the new assignments for this week. In fact, there are two new assignments. One is for coding and one is for theory. Let me go to the theory one first. Now, all the explanations should be here. This is a link to the Google Drive. All right. So the explanation is in this video, and these are notes for the video. I think this is a fairly complete description of what I want you to do. Let's take a look at this one. If I download here, and I take a look at that, you can scroll down and see exercise 1. Notice the names. This was originally taught in Nigeria, so you'll get some cultural enrichment. Exercise 1, exercise 2, exercise 3, and exercise 4. 2 of them are computational, 2 are more theoretical. So I expect the computation ones to be pretty straightforward. You may have trouble with the theory. The point of this presentation is to get you familiar with 2 very important formulas that are used everywhere, both in stochastic processes and in other areas of probability theory. The conditional probability formula and the conditional expectation formula. Conditional probability express probability of an event in terms of conditional probabilities relative to a partition. Conditional expectation, you express the expectation of a random variable in terms of conditional expectations relative to a partition. Now, what is a partition? The intuition of partition is given up here. It's a division of your probability space into disjoint subsets. You see A1, A2, and A3 here. All right, so enough said about the theoretical exercise. Let's go back to the programming exercise, which is here. Do that here. Generating Markov chains from Python, empirical and theoretical probabilities. I want to emphasize that you can look at Markov chains in 2 ways, from 2 perspectives. In one way, a Markov chain should be thought of as a procedure for generating sequences. One very simple example would be flipping a coin. Heads is 1, tails is 0. And each time you run the chain, that's like creating a sequence of 1s and 0s. So we've already done several simulations that are like that. Now when you generate lots and lots of chains like this, then probabilities emerge. And we saw that when we put our sequences into a table and average down the columns to get probabilities. Now these theoretical probabilities are computed using matrix algebra. So you're looking at the same thing from 2 different perspectives. One perspective, you're generating random numbers one by one. And from another perspective, you're multiplying vectors and matrices. So in this exercise, I want to bring both of those together. Number 1, write a program that will generate m Markov chain sequences of length n, given initial probability P0vec and transition matrix PMX. So you will specify the probability vector in the transition matrix, and we will use that information to generate these Markov chain sequences. Now you've generated random walk sequences before. Generating Markov chain sequences are going to be similar, but there's a little bit of added complication. Now store the results in a matrix XMX. Use your matrix XMX to find the empirical probabilities for all states S for all times t. So for instance, if you had a sequence of coin flips, your 2 states would be 0 and 1. And then the nth place of your sequence would correspond to time n. I'm using the variable t. This is a discrete time index, so t equals 0, 1, 2, 3, ... The initial probability vector is thought of as t equals 0. So you're going to use this matrix XMX to generate another matrix called PEMP, where PEMP of ST is the empirical probability of being in state S at time t. So you're going to do column averages but column average is for each different state in the chain. Then it says plot pemp as a heat map using the imshow function from matplotlib.plyplot. You can look up imshow and you can see some examples. So if I say imshow heat map, there should be some images. All right, so here's a heat map right here. And what it does is it's a two-dimensional plot where the color gives you the magnitude of the function. Now in this case we're going to be representing probabilities, so the value of the function will be from 0 to 1. We do have two variables, s and t, so it is a two-dimensional function. And there should be many examples online of how to use imshow. Now, in your code, in order to generate xn plus 1 from xn, you will need to generate a discrete random variable. Remember that the rows of the transition matrix tell you the probabilities of the next states given the current state. So you're going to want to generate the next state using those probabilities. And which row you use will depend on the current state. So for instance, if xn is 3, then you want to use row 3 of your transition matrix to generate the next number in the chain. Now a good way to generate a discrete random variable in Python is as follows. Suppose that the values of the random variable are stored in the array xk, and the probabilities are stored in the array pk. So these would both be one-dimensional arrays. Then the following code will generate instances of the random variable. So I explain this code step by step here. There's a very nice function from the stats package that generates discrete random variables given a probability distribution. So you need to specify the values of the variable and the probabilities, and it will create a random number generator. Then you invoke that random number generator. Here I just need one random number, so I put size equals 1. And the function always generates an array of random numbers, so I need to take the first element of that array. So I explain that in this paragraph. Okay, that's the sequence generation point of view. Now on the other hand, let's look at the theoretical point of view, and we'll generate theoretical probabilities to compare with the empirical probabilities that we found in part 1. Part 2 says, write a program that will generate theoretical probabilities vectors for Markov chain, given an initial probability vector P0vec and a transition matrix PMX. So for each time step, you're going to have a different theoretical probability vector. Store your results in the matrix P theory, where P theory ST is the theoretical probability of being in state S at time t. And plot P theory as a heat map using the imshow function from matplotlib.plyplot. Now so far I haven't given you any specifics. Here are the specifics. You'll run on 3 different cases. This transition matrix in example 110 in Conditional chapter 1. Example 118, there's also an example matrix. And I tell you how many times to run the chain and how long to run it. Right, so you have 3 different examples. 2 graphs for 3 examples, that's 6 graphs. And then I want you to think about your results. Don't just generate it, think about what it's showing. Okay. So question 1, what do the heat maps tell you about the classification of states into recurrent, transient, and absorbing? And comment on the similarities and differences between the 2 heat maps that you generated. When I say 2 heat maps, I mean there's 2 heat maps for each case. So comment on the similarities and differences for the 2 heat maps in each case. I hope that's clear. Please feel free to ask me questions by email or through Hangouts. Okay, that's it.